Okay. Hello, everyone. I'm Saikrishna Arcot. I'm going to be talking about how we manage our Flaky test cases in our Sonic nightly runs. Unfortunately, the original presenter, Zhao Sun, wasn't able to make it today, so I'll be presenting in place of her. Okay. Oops. All right, so I'm going to talk through the pain points of triaging issues that have come up in the nightly test, specifically failing test cases, our solution to that, as well as how we manage the flaky test cases and make them more reliable, easier to debug in the future. So to start off with, in our nightly test, we have 200 test beds that run nightly tests for our sonic images. That is spanning 55 topologies, 70 hardware SKUs, and we have a total of 3,000 test suites that we execute on that hardware. For our nightly run, we have 250 nightly pipelines, which comes out to about 250,000 test cases run every week. Out of that, about 40,000 test cases fail per week. We run these nightly tests because we want to qualify our sonic images for multiple branches. So in the last 6 months, there have been 490 images that we wanted to test and qualify for our production use case. This spans multiple branches, including our 2025-05 release, 2024-11, 2024-05, the master branch, as well as our internal branch that we have with our internal specific fixes, which comes out to, across all those branches, about 2,300 commits in the last year in Sonic Build Image. So with this scale, with the number of failing test cases, that slows things down for triaging issues. 40,000 test cases, not something that one person or a group of people can manually go through and debug. In addition, the failing test log, as well as other data such as syslog, what OS version, all that data is fragmented across different sources, which makes it harder to collect that data and use it to debug, which then leads to repetitive questions such as what image was this run on, what platform was this run on, etc. So to alleviate all of that, we have a pipeline here, this automation workflow. So after every nightly test, an analyzer comes in, takes a look at all of the failing test cases in that nightly test run, and based on that creates an incident in our internal incident tracking system. That then is made visible to a group of people that we call Nightly Guard or Nightly Hawk, who then look at those incidents and then create work items for our other developers to go in and fix. We go through those work items. If it's valid, then it gets assigned to someone to actually work on. And after the issue gets fixed, the whole cycle repeats again. And this is a diagram of what that workflow looks like. So once the test pipelines will upload the test results to a database. The analyzer fetches those results and then stores its analyzed data and its results in a separate database. And that is then made visible to a web tool, which our Nightly Guard team can then use. Now, for the failing test cases that we have, we categorize them into 4 categories. So the first type is legacy, meaning the test case is run in our Elastic test executor, but without retrying the test if it fails. If it fails, then it is considered a legacy failure because this could be something like a baseline test failure that is coming up now and we need to fix it. Second type is consistent. here the test is run with the retry enabled, and so if the test fails the first time, it gets run maybe second time, third time, or fourth time. If they all fail, then it's a consistent failure. Now, if they don't fail, then it's a flaky failure, which is the third type. We'll discuss more about flaky failures later. And then the fourth type, which is decreasing in number, is what we're calling common summary. So this is where the test fails, and all you get back from the message is like something like assertion error or failure, just failed. It's not detailed. It doesn't explain what went wrong. It doesn't explain what failed. It becomes hard to debug, and later we'll see it also becomes harder to deduplicate against other errors, other test failures. We fixed most of those by adding some additional information about what failed, standardizing the error messages so that it's more usable and developer friendly. Now, if we were to just have those 40,000 test case failures become 40,000 incidents and then 40,000 work items, that's not going to scale either. So we need some way to summarize all of that information and kind of reduce the noise so that people can focus on the actual core failures. And so to do that, we have an automation workflow that collects the data, classifies it into one of the four failure types presented in the previous slide, and then we calculate how the pass rate on different platforms, different aspects of the run that I'll go into in the next slide, and then later deduplicate it. So like if we already have a known issue, we don't create a second incident and second work item and just create more work for everyone. Now, the calculation and the filtering. So to better describe where a test is failing, it could be that a test case is failing completely for on all platforms, all hardware on some branch. Or it could be that it's failing only on a specific platform on some branch. And so to better describe that, we have what we're calling like a granularity funneling here. So based on the pass rate of a test case across the nightly runs on that night, or 2 nights or 3 nights, we're looking at, did the test pass for some threshold percentage on all images on that branch? If not, did it pass on that OS version? If not, did it pass on that ASIC? If not, did it pass on that topology? But it's basically to characterize where the test is failing. And then that information is then made available in the example title that you see below. So this title becomes the issue title that gets made visible in the incident, as well as the work item that gets created later that will describe where a test is failing and what the scope of that failure is. So in this case, it's specific to a single hardware SKU in this example. It could also be that test is failing on all branches, in which case, sorry, all platforms, in which case the ASIC and hardware SKU fields might not be there. Now, after we've done that filtering, we need to make sure that we aren't creating duplicates, which would again just be more work, more noise. So the way we do that is we look at the active incidents that are in the system, meaning incident like test cases that haven't been fixed. So first method, compare the ICM title. If the titles are the same in both cases, probably the same failure. Let's not create another one. We know it's already failing. Second method is to compare the summary, which is to say the failing cause of the test case, the failure message. And that is done through this summary aggregation. So we use 2 algorithms. First is TF-IDF, which is term frequency and dash inverse document frequency. Basically saying that the less often a term appears in a sample of text, the more important it likely is. So common words like failure and the and packets, those are all common words. That might mean they're not that important. But instead, if you have something like Arcot table, that's pretty specific. That doesn't appear in too many failure messages. That should be highlighted because that could be like a important factor in what the failure is. Second method is DB scan. So that is density-based spatial clustering of applications with noise, which is basically a clustering algorithm to group together close points of information, and also highlight outliers for future review. We can also use AI at this stage to summarize a test case failure so that the developer who's working on this can quickly get information on what exactly the failure message is and not need to go through thousands of lines of logs to see what the actual failure is. It can also help with the deduplication, which we'll see later, and just generally increase the accuracy of this process. So for example, given 1 week's worth of data, we had 16,000 test cases fail. Based on that, we categorized the failures. We went through the granularity filtering to group together like failures on the same branch, same ASIC, etc. We looked at what the active incidents were. So we saw that some of them already had an incident and the active work item, don't need to create another one. And from that, starting from 16,000 failures, we got 20 new incidents, which is a far more manageable number to handle. Now, this is a screenshot of the web tool that we have that the Nightly Guard, Nightly Hawk team uses. So this is just a list of incidents. Basically, each one represents a test case failure. And from here, if we see that it might be a legitimate failure, we can then create a work item for it to be looked at and fixed. In some cases, it could be that the testbed was not reachable or some failure that repeated across test cases. Those will be handled separately because no point in creating something that is not a true test case failure, like creating a work item for that. Now, in the work item that gets created, we can use automation to fill in some data and set some tags associated with the work item, such as where it's failing, as well as give a table about the summary of results. So in this table, we include information such as what the pass rate for this test case on this branch, on different OS images of this branch, different platforms, different hardware SKUs, different topologies that can help give the person working on this work item a sense of where it is failing, maybe where the issue is, maybe give an initial hint depending on what the failure is. We can also automatically assign the work item to someone based on where the test case failed. So based on what feature the test case is trying to test, as well as what platform it failed on, we can automatically assign this to the right person to look at. This is a dashboard that we've created to track how many test case failures there have been, how many work items that we've created, as well as how many are still active. And this kind of automation lets us collect all failures that are happening in our nightly test. So rather than needing to manually go through the failures or kind of group together failures from different runs, we can use this to look at all of the failures that are happening, try to get 100% coverage, and basically help qualify our images faster and produce better quality images. Now, so the one test case category or failure category I mentioned earlier, such as flaky test cases, the existence of those flaky test cases means that there's an issue in how the test case is written, or there's an issue in the environment, the testbed environment, that is. So that means we need to identify what, why is the test case flaky? What is making it flaky? Surface it, and then try to fix it somehow. Because that would mean that we are not fully reliably testing the software. So to that end, we've created another dashboard that tracks how many flaky test case failures there have been, along with the categories of the flaky test case failures, such as, is it environmental, is it test case specific, or is it something else? And some of the categories of flaky cases might be, as mentioned earlier, testbed environment. It could be that the test order, the sequence in which tests are run are having an impact here. It could be network glitches, such as in our lab network, some packet accidentally got dropped. It could be resource limits, the servers that we are running on. It could be hitting some performance bottleneck, or it could be that the test case itself is not deterministic. It's making some assumptions, which needs to be fixed. And these are the categories, or snapshot of the categories that we currently have for flaky test cases. So yeah, as mentioned earlier, it could be testbed, it could be case specific, it could be multiple, it could be as in some combination of the two. It could be memory on the device being tested. And yeah. Now, because all those flaky test case failures are in some ways easy to identify in terms of what category they might be in, either because of error messages or some other scenario, we can use AI to identify what category they might be in, help with the categorization, and then help with fixing them so that we don't have this issue. So to that end, our call to action is many of the test cases here have been written by the community. So the community, in the sense, is the domain expert for these test cases. So if there's error messages or error handling in the test cases that are missing, it would be great to us to if those error messages were added in or expanded. If there's flaky issues that you see when running these sonic management test cases, create a GitHub issue. If you know how to fix it, even better, create a PR. This will all help us make more reliable releases, sonic releases, help us debug issues faster, and yeah, just help qualify our images faster. So yeah, thank you. Any questions?
Great presentation. Thanks for sharing your information.
Yeah.
You mentioned you use some kind of a density search to identify correlations. I have two questions. One is like, what part of the test logs that you take to feed it through this density search algorithm? Is it the whole sonic management log, or do you extract just the failure message or the error message and feed that through the system?
So I was not involved in that specific part, but if to the best of my knowledge, it would be just just the failure message is what would be my guess, that we are feeding to the system so that we can correlate it with other test case failures.
And the second question is, do you use some kind of metric to measure the efficiency of this correlation match? So like if you iterate and replace the TDF algorithm with, let's say, a newer version of the algorithm, like do you have a way to like compare how is it performing better than your previous version? And is there a quantitative way for you to measure those comparisons?
I don't think we've reached the point of needing to measure it yet. I don't, to the best of my knowledge, I don't think we have a metric in that aspect, but it will be something that will be looked at, yeah.
Thank you.
Yeah.
So are there any plans to upstream the Nighthawk or the dedupe tooling?
Yeah, so right now this is internal to Microsoft. I don't know if there's a technical restriction on making it public. So I'm not sure on future plans to do so or not, but the implementation code-wise is internal to Microsoft right now. But yeah, I don't know of future plans at this time to like make it public yet. Okay. Thank you, everyone.
So where is Louis? Hello, folks. I'm Karthik. And I have, the presentation involves two, Karthik and S. Louis hiding there. The way the presentation is, it's split between the what and why that I'll cover, and then the how is what Louis will be going over. So this is definitely not what I intend to talk about, but maybe the one before. All right, I think we got the right one. Sorry, technical aspects are part and parcel of the presentations. So let me get started. So the discussion is about the modern approach to SOC verification. And the way that we split is the what and why. That'll be something that I'll cover, and then Louis will go over the how. So we all know that chiplets are revolutionizing the whole system design. It's become a cliche right now. And chiplets are the new building blocks of computing. But the main aspect over here that I want to touch on is the modernization of shift left that I'm going to be looking at, which is, as you all know, AI needs to be looked at as a full stack. What I mean by that is it's not just the hardware, it's the firmware and the software components together needs to be looked at. And for that, we need to make sure that we have an aggressive shift left. And this is because we need to have a competitive advantage with things that are churning out from the AI industry. Things get obsolete pretty soon. So what we need for that is three components. We need a pre-verified compute subsystem, early software optimization to be done on those, and of course, the combination of both, which is the co-validation of the software and hardware. Yes, these things are happening right now, but there are aspects that I'll be talking about that gives some credence to this aggressive shift left. And of course, all of this is under the open standards of FCSA, which is our foundation chiplet system architecture that we just released to OCP, the AMBA-CHI, and it's all part of the OCP interoperability guidelines. Currently, we have the shift left taken care of, and this was announced at OCP August 2023 of our ARM Neoverse compute subsystem, which is by far the fastest path to production silicon, and it has proven for partners where they have saved resources and also time and accelerated the time to market. And that being said, it's also the world's leading performant subsystem out there, and it is based off and built on the leading edge technology. Now, this creates the shift left of the optimized compute system, but not yet. We are talking about the full stack that I just mentioned. So what it is, we are trying to compress the time to market from the AI competitive advantage for our partners. So currently we have the IPs, we go to the development approach with the virtual prototyping, which helps with the software development, and then we go into the system integration. We do some shift left, but it helps with the software development acceleration. But no, we need more. So this is where the ARM CSS comes in, and along with that comes our ecosystem collaboration via the ATD ecosystem that we have, where our leading vendors, the supply vendors, and the EDA vendors are part of this ecosystem where they collaborate with ARM and integrate their IPs and their flows to basically accelerate the silicon development timeline with the co-validation piece and the software development all happening together and accelerating the entire development cycle. So this is what we call the modern shift left approach via the optimized CSS plus the ecosystem collaboration that we have via ATD folks. So what does it do? So where we are is we have the CSS, which provides the integrated and validated subsystem. But then with the ARM Total Design ecosystem play, we get an optimized CPU chiplet, which, if you see, is now going to play good with this AI full stack. And this is the acceleration that we are talking about that is coming to fruition. And the next few slides, Louis will be talking about the collaboration that Siemens has with ARM towards this modern approach. Thank you.
All right. Hello. Can I have the clicker?
Oh, sorry.
It's all right.
I just embellished that.
Thank you. All right. Hi, everyone. I'm Luis Rodriguez from Siemens EDA. And we've been thinking about shift left for a long time. It's no secret that, ASIC first-time silicon success has been going down, and the, ASIC projects behind schedule has been going up. The CSS is looking to address this, of course. But we've been thinking about shift left for quite a while, and we've had some success with it in spaces like the SSD market for NVMe, where firmware is very critical to SSDs, as well as CXL. And so based on the success we've had in the SSD market, we're bringing this to the ARM ecosystem through the ATD partnership. And the basic building blocks are starting from standards-based verification IP. So my team has been doing verification IP for over 20 years. It's all standard-based, so things like AMBA, CHI, AXI streaming, low-power interface, but also PCI Express, CXL models. These are fully system Verilog class-based VIPs that can be dynamically configured. You can use them for error injection. You can randomize behavior to get high coverage. And so they're typically used at the IP level. But now we want to bring it into the system level, at the CSS level. And the way we do that is through system C integration through TLM. And so we're able to build an adapter or shim layer to the VIPs that can connect to an ARM fast model. And so now we're able to bring this ARM fast model. So here you have a CSS with, it's a little bit abstracted away. You can see the main blocks like the CMN, the IO macro block. And just based on what I was showing in the previous slide, we can now bring the ARM fast model into a simulation. So on the right, you have RTL code. The block that just appeared, that's the one I was showing before. You have an ARM fast model through TLM ports connected to verification IP. And then we can keep building this out. We have the infraboard FVP here, very similar, connected through TLM to the AXI VIPs. And you can connect things like we have a PCI Express subsystem that's pre-validated, SBSA compliant, built. Again, this is the system Verilog VIP with some additional adapter code. And so at this point, you're actually able to load UEFI and UEFI image, do the whole boot up process, start running test cases like SBSA, and prove that your system that you might have configured differently from the out-of-the-box test bench. So you have made some configurations. This allows your firmware team to start validating firmware. It also allows you to run SBSA test cases and other interrupt test cases. And then, of course, at this point, you might have other teams that are working on, for example, PCI Express IPs at the block level, and they can start also substituting VIP for IP blocks and take a modular approach to bringing up your CSS. You can also model multiple chiplets, through PCI Express or UCIe. And again, you can use a combination of IP and verification IP to model this. And there's multiple advantages, of course, doing this shift left approach. It allows your firmware teams to start working earlier on the firmware. It allows your hardware team to collaborate with the firmware team during the debug. So you're running RTL simulations. You can do waveform dumps. You can do step-through debug. So we do support setting breakpoints in the firmware or software, and we will pause the RTL simulation. And so you can do step-through debug. And it runs faster than you might think. We've done a lot of optimization to this software-aware VIP. And so right now, we're able to run about 800 million instructions, which is about as much as it takes you to get to UEFI in less than 2 hours. And you can just see an example of dumping out a tarmac trace. And on the right, you get the verification IP tracker files that show you information at the FLIT level. And yes, so do you want to do the call to action?
Sorry. So there's a call to action for contribution towards this shift left flow that I just presented. If you see something that is inherent that is not there, called out, please let me know. And other than that, there is a BSA, SBSA compliance program that we have, pre-silicon compliance program. So please do contribute to those. And as I just mentioned, we have provided the FCSA spec to the OCP community, so requesting contribution towards that.
All right. And additionally, we could not bring this shift left methodology without a lot of the open standards. So we've collaborated to PCI Express, CXL, UCIe specs, a bunch of wires as well. It requires things like contributing to QEMU as well for specific applications and being able to also debug the open source UEFI code. So all of these pieces are brought together into this methodology. And finally, we're very open to partnerships, and so you can reach out to us either through the ATD partner program or directly. Thank you.
Thank you. Any questions? Anyone? All right, thank you guys. So either I did a
Thanks, everyone.
bad job or